Thank you very much. It's a great pleasure to be here. I spent 3 years at different very good American universities, and I would not have had the career I've had without those experiences. I'm really grateful to American universities. I represent the Wallenberg Wood Science Center. It's funded by a private foundation in Sweden, and they have helped us to focus on more fundamental issues, although during the last couple of years we've tried to see if there is something that we could actually use as well. On the left-hand side there, it's a very interesting book about, let's say, the life, biological life in your sequoias. And these are huge organisms. 110 meter, you have one tree that in Sierra Nevada that is 110 meters in height, 10 meters in diameter. And the only reason this is possible is that I think it's probably 1 or 2% of the tissue that is alive. The rest is dead. So it's a very efficient way of building a large structure. I think the age could be something like 2,000 years of these organisms. It's quite impressive. So on the right-hand side there, you see the cell wall. So my main research interest is really the nanostructure of that cell wall and how to manipulate it. So this is an example of a recent application in Sweden. I think we can learn from these new uses of wood and try to push the performance of our material. This is very promising technology, and I hope it's going to... So there's one unit up and several in the pipelines. So I will focus on modulus, trying to understand modulus of these materials. The reason I will not talk so much about strength is that it's very difficult to use strength as a material property. If you look at the bottom there, you see that we have many scales, and strength of a given material will be different if we measure strength of a beam or if we measure the strength of a wood film, for instance. So that's why I focus on wood, which is more easy to predict based on fundamentals. So essentially, relative density is a very important concept here. Essentially, the modulus, the longitudinal modulus of the composites of the wood scales with the relative density. So straightforward, the more tissue you have, the higher the modulus of your material. And if you look on this image here, this is data from a large variety of species. And if you back calculate the modulus of the cell wall, it ends up with 35 gigapascal. And the reason you have some scatter is because of anatomical differences between species, but also this microfibril angle, the angle at which the stiff cellulose fibril is oriented with respect to the longitudinal axis of the cell. I also wanted to point out that it's not only about tensile properties. It's many times we load structures in bending, and then so this is the point, this is the point at which the load is applied. And as you can see, there is substantial local strains, and that's because the beam fails in compression, because the compression strength is much lower. So the compressed wood that Bing is working on is very favorable in this respect. You can address this problem. And also if you add polymer matrices, you can address this. So there is some, in addition to Bing's work, there was some early Japanese work. And So this is Young's modulus as a function of density of the material. The circles here are without any resin. So if you take the comparably high density, 35 gigapascal, you get a modulus of the cell wall, which is around 40 gigapascal. So that's perfectly reasonable to get that from compressed wood. And the reason is the high properties of the cellulose fibrils. So I will go through a couple of chemical treatments that we've been using. Sulfonation has been of interest because if you want to use ion conductivity, then sulfonation provides such mechanisms. So in this case, we were able to get a density of 1260 kilos per cubic meter. And then the cell wall modulus is 36 gigapascal. And we're sort of utilizing the realization in previous work by being that if you keep the lignin there, you have a resin which is intrinsic to your material. So at that stage, you can get something like 36 gigapascal. If you then use oxidation, so that's a different procedure where you remove all of the lignin essentially. And the idea is to separate the microfibrils. So if you look at, so this is data from small angle X-ray scattering, and this is the interpretation. So the microfibrils are embedded in lignin and hemicelluloses, and in the initial state, they are close together. We have a distance between them of 4 nanometers. With the enzyme oxidation, and of course, the purpose of using enzymes is that we have a highly eco-friendly method of chemical treatment here. We don't need chlorine compounds. Then we separate them, so the correlation distance is 10 nanometers. And the reason is that we have these carboxyl groups, which have electronegative charge, and they repel each other. And if we then make materials out of this, if you look at on the left-hand side here, you see the fibrils are separated at very small scale. You can see that they are individualized. If we look at the cut surface, you see they are clearly individualized. So in principle, from a mechanical behavior point of view, that should be advantageous. We have individualized fibrils that will fail as individuals. And we get quite high density, and the modulus of the material is 54 gigapascal, and of the cell wall then, it is 60 gigapascal. So we're really approaching, I think, what is technically possible by controlling the nanostructure of the cell wall. And I think this is one very important aspect. Even though we're dealing with large structures, beams, we have unique possibilities here because we can tailor the nanostructure and we don't need to assemble a material bottom up. We can utilize the existing nanostructure from nature and try to manipulate that for our purposes. And this is the last example where we have a composite, and the composite is prepared by first preparing a so-called serogel. It means that we can dry it at under room temperature condition, ambient conditions, and we generate a highly porous material, which we compress, fill with a polymer. And these are the modulus data for different wood contents. And if we use a similar, very simple theoretical approach, we end up again with a cell wall modulus of around 60 gigapascal. So that seems to be reachable. So this is very recent work addressing the problem of, so delignification could be an interesting possibility to create new wood materials. A problem is if you try to do that with thick structures, you end up with pulp at the surface and no chemical treatment in the center. So what we have done then is that we use sub-zero alkali. And if you look at the left-hand side image, you have very thin cell wall, whereas with the same scale bar, you have significant swelling of the cell wall. And this is dramatic. Several times the original thickness. It means that we have a large amount of nanoscale porosity, which opens for manipulation of the material. And what we did was that we filled this, we prepared successfully samples. We did chemical treatment filled with a polymer. And if you look at the images here, you can note that the cell wall is swollen, and we are able to remove some of the optical defects that can otherwise cause problems with transparent wood. And this is the proof. This is electron diffraction. On the left-hand side, you have native wood and PMMA. On the right-hand side, we have the specially treated composite. And the dark regions means that we have impregnated the cell wall with the polymer. So we have a nanoscale composite by using this procedure. If we look at the optical transmittance data, they are significantly improved. So in order to get good data, you need to measure transmittance for several different thicknesses. And from the slope on the log scale here, we see that the only material that is doing better is the material based on sawdust. So we think this is very promising. I complained about tensile strength as a concept, so what can we use instead? And when you design large structures, then fracture mechanics is very helpful. And I wanted to quickly present some methods, but also address the issue of why is it that we perceive wood as such a tough material? So on the left-hand side, you see microscopy studies of a crack growing in wood, and the fibers are in the horizontal direction, and we're trying to grow the crack in the vertical direction here. But as you see, it deviates all the time. It tends to go to the sides here. And we then used numerical analysis of this mechanics problem. And on the top, you have experimental data. So we're locally measuring the strains. This is for birch. This is for unmodified birch with the polymer, and the delignified birch with the polymer. So these are the experimental results. We look at the damage mechanisms at the crack tip, and then we model this with finite elements. And the procedure we're using is that we have start values, and then we use the local strain fields, and we know the global stress. So then we can update the material properties, which is a reasonably complex problem because it's an orthotropic material with several elastic constants. And the difference between the predictions and modeling are reasonably good, except for maybe the birch case. So this is how we set up the problem. So essentially, we're driving a crack. We have one failing law for the transverse crack and one for the crack propagating. And if we look at the data, we can conclude that the toughness is about twice as high for the composites, and it doesn't matter this nanoscale tailoring for this particular property. Whereas in the other direction, when it grows like this, the material is really, really weak and brittle. So it appears, if we look at the if you look at the tree stem that is broken, that one of the reasons we see this toughness is that there is such an enormous large volume of the wood material that is fracturing. We have cracks all over the place. And it's sort of a paradox that one reason is that the material is really weak in one of the directions, and that is causing these complex energy absorption processes. I wanted to finish off with very simple. We've done a lot of nanoscience manipulating the cell wall, and I will give 3 very quick examples. The first one is we put quantum dots in there. We use it for LED lighting. And the key science point is how do we get them into the cell wall? The second one is we precipitate plasmonic nanoparticles. The same thing, we bring them into the cell wall. We try to control particle size. Next example, metal salts treatment, the same thing, trying to get them into the cell wall. And the third example, we use a bio-based resins and we put a phase change material in there. So it's like a thermal battery. We can store heat in the material itself. And again, we're manipulating the cell wall. That's where the science is. And I think that this is really an important field to find key problems we can address and utilize this. There are several applications today where, let's say, the function is derived in a very simple way. So you can buy these magnetic wooden knife holders, but it's just magnetic film bonded to the back of the wood. Lighting, you bond LEDs into the wood structure, and this is carbon fibers into a beam to provide electrical conductivity. But now we have possibilities to provide these functions in a very controlled way and utilizing the nanoscale structure of the cell wall. And I think that's what we should utilize, try to focus on. So summarizing, we now understand the limits of cell wall properties of these materials. I think the sub-zero sodium hydroxide treatment is something that can facilitate scaling of nanoscience achievements to somewhat larger scale. Polymer filling is addressing many of the limitations of wood, but of course it has disadvantages. But it gives us another tool in our box. I talked about the toughness issues. Finite element updating is really suited for a material like wood because it is more complicated than isotropic materials, and then we can use this in a very straightforward manner. And I want to finish off by saying that I recently went to a wood modification conference where most of the researchers are funded by companies, and they all talked about heat-treated wood. And when I teach, I use a textbook from 1964. So somebody from the Forest Products Lab wrote this book. It's fantastic. Everything you need to know about heat-treated wood is in there. And there is also a section about compressed wood. But I think this is the opportunity we have to use modern techniques, nanoscience, understanding of how to bring science to technology. And I think this is good timing for that. Thank you very much. We'll get time for one.
Lars, really enjoyed your insightful talk. I would like to pick your mind to get your prediction of the upper limit of the stiffness of a compressed wood. Can we go beyond 100 gigapascal, 200 gigapascal? If we're not there yet, what need to be changed in terms of the material structure or the composition ratios of the 3 components of the densified wood? Thank you.
Yes, if we want to go to 200 gigapascal, we need to add another component. There's no way we can get there with cellulose. So maybe one should focus on other aspects of the properties of wood that, and I think in particular, we have unique possibilities to provide multiple functions since it's initially a porous material. So we can do all kinds of sophisticated modification.